Okay, all right, carrying on with some of our acid reactions here. We were looking at acids and carbonates. So the second example problem here, we've got H2SO4, so that's our acid, that's sulfuric acid. Sodium hydrogen carbonate, that's our carbonate. So again, acid and carbonate, we know what the products are going to be. They're going to be CO2, which is a gas, water, which is a liquid, and a salt. Now, the salt, the anion, is going to be sulfate, that's coming from our acid. The cation is going to be sodium, that's coming from our carbonate. So the correct formula for sodium sulfate is Na2SO4, and that, as a sodium salt, is going to be aqueous. Now, you've got to get the right formula there again. Like, so we know sodium is a +1 cation, we know sulfate is a -2 anion. So to get the right formula, the positive and negative charges have to be balanced. 2 positive charges, 2 negative charges, Na2SO4. If you just have NaSO4, it ruins the entire reaction. So again, it's very important that you get the right formula there. Now, we want to balance out this equation as well. So 2 hydrogens from the acid, but we need to remember hydrogen is coming from the hydrogen carbonate here as well. So at the moment, I've got 3 on this side and 2 hydrogen on this side. That does not work. So something's going to have to change there, but because hydrogen's in 2 different places back here, I'm not sure exactly what to change. So let's hold on to hydrogen and look at some of the other pieces and see if that solves our hydrogen dilemma. So sulfate in H2SO4 stayed as sulfate throughout the reaction. There's no other sulfur containing component here. So I'm going to treat sulfate as sulfate here, and that will help minimize the complexity of counting the oxygens in the other parts of the reaction. So there was 1 sulfate here, there's 1 sulfate there. That's good, and I'm going to leave those oxygens out of my other total count. Right? Unless I have to change either H2SO4 or sodium sulfate. Only 1 sodium here in sodium hydrogen carbonate, but again we said we needed 2 for sodium sulfate, so I'll need a 2 here for sure. That gives me 2 sodiums, that's good. Now this has the added advantage now of giving us back an even number of hydrogens. 2 from the sulfuric acid, now I have 2 from the sodium hydrogen carbonates. So that's a total of 4, so I can balance that by putting a 2 in front of the water there. That just leaves oxygens, okay? And not just oxygens, remember we already balanced the sulfate, so just the oxygens from carbonates, CO2, and water. So 2 sodium hydrogen carbonates, that would be 2 carbons and 6 oxygens. So to get to 2 carbons, I can put a 2 there in front of carbon dioxide. 6 oxygens, now I've got 4 there, 2 more there, that's my other 6 oxygens. So 1 mole of sulfuric acid reacts with 2 moles of sodium hydrogen carbonate. That'll make 2 moles of CO2, 2 moles of water, 1 mole of sodium sulfate, and that equation is balanced. So that's the kind of application of not just knowing the reaction, but also understanding all of these formulas and how to balance an equation that I'm going to want to see when we get to testing on this topic. Okay, the last acid reaction we're going to talk about, and then there's still one other type of reaction we need to talk about this chapter. It's called an acid-base reaction or a neutralization reaction. So we said an acid has hydrogen in the front. There's actually several ways to define what an acid is and several ways to define what a base is that we'll start to look at with more complexity as we get more into that chemistry, primarily in the second semester if you go on to take Chem 2. For our purposes at the moment, we're going to say an acid has this hydrogen that it can donate, right, as H+, and a base has hydroxide ion in it. So this is the simplest definition of acids and bases. H+ donor, OH- donor. And the form of an acid-base reaction, at least in this version of acids and bases, is acid plus base. So HCl here is our acid. NaOH, or sodium hydroxide, is our base. These reactions always give water and a salt. Okay, so in this case, we're getting H plus from the acid and OH minus from the base. That's where the water comes from. Acid leaves behind an anion, chloride in this case. Base leaves behind a cation, sodium in this case. So our salt here in this one is sodium chloride. Okay. Now, H3PO4, that's phosphoric acid. It's going to react with potassium hydroxide. Right? So this is acid base. That means one product is going to be water, which is a liquid. The other product is going to be the salt. Now the salt in this case is going to be potassium phosphate, which is K3PO4. And that again is something you need to be able to do from information we've already talked about, is identify that formula. That's a potassium salt, so it will be soluble. So we want to write aqueous there in the balanced equation. Now, once you get the products, we need to balance it. Right? Now, a good place to start here might be with potassium. Since we know we have 3 potassiums over here, that means we need 3 here in front of potassium hydroxide. If we have 3 hydrogens coming from the phosphoric acid and 3 hydroxides coming from the potassium hydroxide, that means we should end up with 3 waters, because we get 1 water for every hydroxide and hydrogen, H plus, that combine. So that would be 3 plus 3, 6 hydrogen, 6 hydrogen there, 1 phosphate here, 1 there, 3 potassium there, 3 potassium there, right? 3 oxygen there, 3 oxygen there. So that balances. Okay. The other example here, HNO3 is nitric acid. MgOH2 hydroxide there, that's our base. So again, you see acid base, you should think, oh yeah, water and a salt. So H2O, liquid. Right? And then we've got to figure out the salt from the pieces. Now the salt in this case is going to be magnesium coming from the base, nitrate coming from the acid. Well, magnesium is a +2 metal. Nitrate, the polyatomic ion, has a -1 charge. So that is going to be 1 magnesium and 2 nitrates in the formula. But nitrate salts are always soluble, so we should know and be able to identify that as aqueous there. Okay. Hydrogen coming from the acid is going to combine with hydroxide to make the water. So we have 2 hydroxides from magnesium hydroxide. We should have 2 equivalents of the acid. That'll be enough to make 2 waters. Right? That also gives us 2 nitrates, which show up in our product as well. So nitrates here are also balanced, 1 magnesium, 1 magnesium. Right? And the hydroxides also contributed to the water. So 2, 1, 2, 1. And that equation is also balanced. Okay, so keep those 3 equations in mind, as well as predicting the precipitates when you're mixing solutions together. You should be prepared to tackle all of those equations, right, and have a good idea of how to get to the products, figuring out the products, and correctly identifying and writing out everything that happens in those equations. Okay, there is one more type of reaction we want to talk about, so let me just introduce it a little bit here at this video, and then we'll mostly start covering it in the next video. The last type of reaction we want to evaluate, at least in this chapter, is called an oxidation-reduction reaction. So in this type of reaction, there's 2 processes going on, oxidation and reduction. And defining those might be a good place to start. So we can do that right here at the tail end of this video. Oxidation is the loss of electrons. So if we have a species in our equation that's losing electrons over the course of a reaction, we might describe that as oxidation. Reduction is sort of the corollary there. Reduction is gaining electrons. So, same thing, if something in our reaction lost electrons, those electrons have to go somewhere. They end up associated with something else in our reaction. Right? So what we want to be able to do is identify if something is an oxidation-reduction reaction, identify what was oxidized, what was reduced in that reaction, but we also want to be able to recognize if a reaction is not an oxidation-reduction reaction, if no electrons are transferred. And that's what we need to talk about next, is how we can identify those things. So that will come in the next video.